For problem number 4, we've got a large conducting plate with positive charges, and it has a constant charge distribution of sigma, 6 microcoulombs, so that's times 10 to the negative 6. And it says calculate the electric field in region 1 and region 2. So we want to make sure that when we create our Gaussian surface that the electric field lines are perpendicular to that surface, and therefore the surface area we're going to use are the ends of our cylinder in our Gaussian equation. So we're going to start with our Gaussian equation, E dot dA is equal to Q enclosed over epsilon naught, and our surface area is pi r squared, but we do have 2 of them, so I'm going to multiply that by 2, and then we need to figure out our Q enclosed, so I like to do that work separate because that's often, occasionally a lot of work. So sigma is given to us as a numerical value, and that's an ugly sigma, but you know what I mean. And we have Q is equal to charge over area. Well, when I am looking at the area that is enclosed for a conductor, I've got the circular surface area on one side and the circular surface area on the other side. And obviously drawing 3D is hard, but I need to include both of those. So the area is also 2 pi r squared. So you're going to notice this for charged planes is that the area always ends up canceling out. When I plug in this expression to my Q enclosed, oops, that ends up canceling out, and I have an electric field of sigma over epsilon naught. When I plug in my values of 6 times 10 to the negative 6 over epsilon naught, which is 8.85 times 10 to the negative 12, I end up getting a numerical value of 6.78 times 10 to the 5th power, and that's newtons per coulomb. And that is the electric field of this side and the electric field of this side. So they both have an electric field of 6.78 times 10 to the 5th. So I can put that for both, and also the same for region 2. The next problem we started in class, and you kind of continued it for homework, is when we have another charged plate with charge density rho of negative 6 microcoulombs. Then how can we find the electric field of these 3 regions? So they're equal and opposite charge, and what we want to think about is the fact that if I know one plate is going to give me an electric field of, I'll call it sigma over epsilon naught on this side, I also know it's going to be sigma over epsilon naught on the other side, and then for this negatively charged plate, we're also going to get and the arrow there should be in toward the negative, sigma over epsilon naught. So what we want to think about here is direction. And when we add electric fields together, like we have an electric field from region 1 and region 2, then we also have to consider whether they need to be added together in magnitude because they're going in the same direction, or added or subtracted because they're going opposite directions. So conceptually, I want you to take note that the electric field of a plate gives us a constant value. So for all of the other charged objects, distance was a factor, and it either electric field either decreased when it was further away by factor inverse squared, or by an inverse proportion. So we need to know that for plates, the electric field does stay constant. The lines do not change in density. They stay exactly the same whether I'm all the way out to infinity or really, really close to my plate, which is opposite of a charged sphere or a charged cylinder. So what you also want to notice is that if I have electric field lines going out of the positive plate, it's going to go out to infinity, which means it's going to continue outward even on this side to the right side of my negative plate. And same goes for the negative plate. I'm going to have the negative fields not just start here in the center, but they're going to come in from infinity and go into the negative plate. So we are going to take those directions into consideration. One thing I want you to notice is that on both sides, and let me get rid of all these lines first. What I want you to notice is that on both sides, we have the same magnitude of electric field. And as I stated, this electric field that is going to the right here is also coming in from, or sorry, going into the right, coming in from the left, is also coming in from the left on this side. So the magnitude stays the same, except the direction is different. So let's, for the sake of clarity, call right positive and left negative. I'm going to call this a positive value. This is also pointing to the right, and so that's a positive value. This right here is pointing to the left, so that's a negative value. And this is pointing to the left, so that is also negative. I want to show that the negatively charged plate here has electric fields pointing to the right, so I need to add that sigma over epsilon naught. And I want to show that this positive plate continues its electric field to the right on this side, so I'm going to show that as a positive. And if I add these together, we call this superposition. The positive and the negative here cancel out, so I have an electric field of 0 in region 1. I get the electric field that adds together in magnitude, so I get double my electric field in region 2. And if I doubled my 6.78 times 10 to the 5th, I would end up with 13.6 times 10 to the 5th for region 2. And then for region 3, same thing happens. Everything cancels out, and the electric field in region 3 is also 0. So you can analyze it in that way. Another thing students like to do, which I'm going to get rid of all of this at the top just to give you a different way of looking at it, is you can use a Gaussian surface. At least this works for region 1 and region 2. You can use a Gaussian surface that goes all the way from the left side of the positive charge to the right side of the negative charge. And in that scenario, we can see that our Q enclosed is equal to 0. And if I plug that into my expression, I can see that if that's equal to 0, then the electric field is also equal to 0. So if you look at, there's 4 positive charges on the left, which equals the 4 positive charges on the right, then we end up canceling out our electric field that comes out of this side and this side. And now we know conceptually why that happens. D is calculate the electric force on an electron placed in the region Well, this again goes back to our kind of fundamental principle that E is equal to F over Q, which means force is equal to E times Q. They don't give us the charge of an electron, but that's something, sorry, this should be E. That's something you should be able to calculate. I'm messing up my variables. This should be F, this should be E. So we've got 13.6 times 10 to the 5th. Look in your equation sheet for the elementary charge. Actually, I don't even have it off the top of my head. I believe it is 1.16, but let me look it up really quickly. It's 1.6 times 10 to the negative 19. And then you solve that and you get 2.17 times 10 to the negative 13 newtons. And again, does it depend on the electron's location? No, because we established uniform electric field for charged plates. Distance does not matter in these scenarios.